All right, again, just to reiterate the plan for the next couple of days, today we're going to begin section 4.3, and then I'm going to try to get to as much as I can today, and then try to finish the notes tomorrow. We'll see how far I get through today, and then we'll finish the notes for tomorrow, and then hopefully on Thursday, we have a work day over section 4.3. No matter what, I should only need a little bit of time on Thursday, if any, to finish the notes. So you should have a majority of section of Thursday to work. All right, so just like we were talking about, the derivative plays a vital role in telling you about the look of the graph, right? The derivative plays a key role in telling you how the function acts, because the derivative is truly the slope. Don't lose sight of that. We've studied the derivative so in depth in chapter 3 that sometimes we get too far into it and we lose sight of what the derivative actually means. The derivative is slope, right? If you can calculate the derivative at any point in time, that is the slope of the tangent line at that instantaneous point. Okay? To see how the derivative of f can tell us where a function is increasing or decreasing, let's take a look at figure 1 over here. Now, what you're not seeing, you maybe not see it very closely here, there's little lines in here. And basically what I'm doing is I'm taking the slope of the tangent line at each one of those values. Remember, the slope of the tangent line is equivalent to the derivative. So what do we notice here about the graph? That every time the function is going up, at every point the function is increasing, look at the slope. It's positive, right? The slope is positive at every point the function is increasing. And when does it lie flat? At the local maximums or minimums, right? That was the theorems that we learned back in section 4.2. It's going to lie flat at every peak or valley. The slope will. The function, the derivative of the function will be 0 at every peak or valley. And then as soon as it starts to turn back downward, the derivative starts to turn negative. The slope starts to turn negative. So I'm going along here and I'm saying, okay, up, 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 up. And then as soon as I get to here, my slope is flat. And then as soon as I start turning down back toward the minimum, my slope goes negative. And then it's continuing and continuing until it reaches that local minimum point. And then the slope starts to change and go back up, right? So I can say this. Every point the function is increasing, the slope of the line is positive. The derivative is positive. At every point the function is decreasing, the derivative is negative. The slope of the line is negative. So we can have this thing called the increasing-decreasing test, or I call it the ID test because I'm lazy. The ID test says that if f prime is greater than 0, if f prime is positive at any point, then that function is increasing on that at that point. Okay? So if I can choose some interval, I can say, take a look here. I know at B there's a critical value. There's at some point B a critical value. We know how to find that. That was all section 4.2, right? We know how to find that critical value. Every point to the left, as long as this is continuous, every point to the left of B is going to have a positive slope, right? Every point on the left of B is going to have a positive slope, without exception. Every point between B and C is going to have a negative slope. And every point from C to D, and C onward, I guess if this continued onward, it would have a positive slope again, right? So to see, because at this point, it's really ambiguous. We can find those critical points, but we have no idea if there are local maximums or minimums, right? Section 4.2 got us to knowing where those critical values are, but not really knowing anything about it. We don't know what's happening around it, but we at least know that there's something funky happening at those C values. What we can now say is that if I look to the left or right of those C values, I can then determine if there is a local maximum or a local minimum by looking at the value of the derivative at those values. If the value of the derivative is positive, then I know that function had to have been increasing. We can see that from the graph in this one, but a lot of times we don't have the graph. if the derivative is negative, I know it's decreasing at some value in between there. Okay, and I know if the derivative is 0, then that's a critical point. So take a look here. Please copy this one down because this will tie directly into example 2. So make sure that you have this one because the work is going to just copy and paste over to example 2. Find where the function is increasing and where it is decreasing. Find where the function is increasing and find where the function is decreasing. Now, to figure out where the function is increasing and where it is decreasing, I first need to figure out where the critical points lie, right? Because that will tell me where it shifts from increasing to decreasing, or the possibility of them shifting from increasing to decreasing. I have to find the critical points, critical values. Okay, now the critical values are where the derivative is equivalent to 0 or where the derivative does not exist. All right, so f prime of x is equivalent to, oh, perfect, this is polynomial. It's an easy derivative. 12x to the third minus 12x squared minus 24x flat. That's the derivative. So let's basically just find the derivative, find the roots of that function. All right, looks like I can pull out an x, right? Oh, even better, a 12x. Let's make this a little bit cleaner. 12x. I'm setting this equal to 0 now, right? Let's pull out a 12x. That's going to turn into x squared minus x minus 2 equals 0. Which factors? Factors of negative 2 that add to get to negative 1 are negative 2 and positive 1. So 12x, x minus 2, x plus 1. So the critical values to this function are 12x equals 0, x minus 2 equals 0, x plus 1 equals 0. I don't know why I wrote that because it's just 0, 2, and negative 1. Those are all of the possibilities where there could be a turning point. Now, I didn't even think about the fact that the derivative could not exist. And why didn't I think about that? Because it's polynomial, right? There's no places where the derivative does not exist. You only think about, they only worry about that when it's rational or when it's a square root function or when it's a root function. All right, now, here's what I have. I have 3 places where I know there's a possibility of having a local maximum or local minimum, or where it could go from increasing to decreasing. So here's what we're going to do. We're actually going to create a little number line, okay, to see where there could possibly be increasing to decreasing shift. We know that there could be, oh, I have 3 points, not just 2. Come on, Myra. There could be a shift at 0. There could be a shift at 2. Oh my gosh. Can we put them in order on a number line? Negative 1, then 0, then 2. Come on now, Laverick. Okay, negative 1, 0, then 2. Now, how do I know whether there's a local maximum or a local minimum? Because I can't tell. I don't know. Maybe you guys are better at math than I am. I can't tell where there's local maximums and minimums. I know something funky is happening at negative 1, 0, and 2, but I don't know what. The only way to do that is to figure out what's happening around it. So here's what I'm going to do. I'm just going to pick some points. Please, can I have blue? Thank you. There we go. Let's pick negative 2. That's a good point to the left of negative 1 to figure out what's going on. Let's pick negative 0.5 in between negative 1 and 0. And let's pick 0, between 0 and 2, let's pick 1. And then beyond 2, let's pick 3. Because wouldn't you agree that any point in between negative 1 and 0 is going to have the same value, whether it's positive or negative, right? If I pick negative 0.5 and it comes out positive, then every single point in between negative 1 and 0 should still be positive. If I pick a number between 0 and 2, say I pick 1, any point should be positive or negative if 1 is positive or negative. They should all have the same sign. All right, so now what I do is I run that through the derivative. And again, you're going back into the derivative, okay? because the derivative is going to tell you the slope of the line. So let's see what happens when I plug in negative 2. 12 times negative 2 to the third power minus 12 times negative 2 squared. 12 times negative 2 to the third minus 12 times negative 2 squared minus 24 times negative 2. Parenthesis. I don't care about the fact that it's 96. I care about the fact that it's negative. I care about the fact that it's negative. This turned out to be a negative. Now, I would bet that in between negative 1 and 0 is probably going to turn out positive, but it doesn't have to. Let's see what happens, though. Okay, in between negative 1 and 0. Well, in this case, I've got negative 0.5. So 12 times negative 0.5 to the third minus 12 times negative 0.5 squared minus 24 times negative 0.5. Came out positive. I don't care about the fact that it's 7.5. I only care about the fact that it's positive. All right, and let's choose 1. Well, 1's a pretty easy number to plug in. This is going to be 12 minus 12 minus 24, right? 12 minus 12 is 0, minus 24, negative. It would be negative 24, but I don't care about the fact that it's 24. I care about the fact that it's negative. And then we check 3. Now that I got to plug in. 12 times 3 cubed minus 12 times 3 squared minus 24 times 3. Just double check that. 12 times 3 cubed minus 12 times 3 squared minus 24 times 3. All right, 144. 144. Positive. 144. Now, what does that tell me? That tells me that the function is decreasing. If it's a negative sign, the function is decreasing. It's decreasing at all points to the left of negative 1. So it's decreasing from negative infinity to negative 1. Not inclusive. I can't include that because is it still increasing at negative 1? No, it's leveled out. It's increasing at all points between negative 1 and 0. Now, don't do your test points. Your test points, we picked those out of thin air. Those could all be different for everybody because we just picked those. Go with your critical points, critical values. And then it's decreasing from 0 to 2. It's a negative sign from 0 to 2. And then it's another positive sign from 2 onward. So it's increasing from 2 to infinity. Yes, sir?
How do you know that again?
Based on the signs. It was negative.
How did you get the signs?
We plugged in negative 2.
Okay.
Yeah, that was me doing these calculations. Since it was negative 96, I knew that it was going to be negative. Since it was positive 7.5, it's positive. 1 we did by hand, and then 3 turned out positive as well. Okay? Yeah, and you go back into the derivative, not the original. And that's a key mistake that a lot of people do. You don't go back into the original, you go back into the derivative because you're looking for what's the slope doing. This is all negative slopes. This is all positive slopes, negative slopes, positive slopes, which tells me what's happening with the function. It's decreasing because the slopes are always negative from negative infinity to negative 1. And then at negative 1, it shifts. It shifts at negative 1 and then starts increasing again. And then it stops, and then it starts to decrease again. And then it stops, and then it starts to increase again. Okay? And that's telling me about the original function. Now, I think you might be able to see where we're going with this. The ID test, the increase-decrease test, will then really let us know what's happening. Because if a function is decreasing and then it starts to increase, wasn't that a local minimum? Like, isn't that the definition of a local minimum? I'm coming to a bottoming out point. If the function is decreasing and then it starts to increase, there must be a local minimum at that value. That is what's called the first derivative test. You say, okay, suppose that c is a critical number of a continuous function. We just found the critical points, right? It was 0, -1, and 2, right? If f prime changes from positive to negative on the left and right side, if it goes from increasing to decreasing, if it goes from positive to negative at c, then f is obviously a local maximum. If it's increasing and then starts to decrease, then it's got to be a local maximum. If it's negative to positive on either side, it's going down and then it starts to come up, then it's got to be a local minimum. It's got to be a local minimum. If f prime is positive to the left and right, that means that there was a bend in there. There was a place where it leveled out. There was a critical point at where the slope ended up being positive, or slope ended up being 0. However, it went up, leveled out, and then continued to go up again. That's like our friend, the cubic function, the basic cubic function, where it goes up, levels out, and keeps going, right? That's a cubic because it's increasing, leveled out, and then just kept increasing. It didn't go back down. It kept increasing. If that's the case, there is no local maximum or minimum. So if you get to a number line and it's positive, critical point, positive, that's not a local maximum. That just means there was a bend there. Same thing if it was negative. If it's negative to the left and to the right, then it would be going, okay, decreasing, leveling out, still decreasing. Okay, it does not increase back up again, so therefore there's no local minimum. It just keeps going down, just kind of like snakes down. It goes and bends down and then goes down. Let me show you some graphs. Whoa. Come on. Let me show you some graphs. Here's what I mean with the first derivative test. We're finding, like the first part is finding the critical points, like finding what is that C value? What is that C value? What is that C? Because these are all critical points, right? When you find the critical points, you're looking at places where it could possibly be a local maximum or minimum, but not necessarily. And we talked about why a lot. See here, okay, the slope was positive and then it turned to negative. I know there would be a local maximum at that point. The slope is negative and then it turned to positive. There's got to be a local minimum at that value. The slope is positive and then positive, not a local minimum or maximum. The slope is negative and then negative, not a local maximum or minimum. We do know that it bends in there, which is something that's important, like something that's a useful piece of information when we go to graph, but not necessarily telling us about any sort of maximum or minimum values, okay? So let me go back and say, okay, find the local maximum and minimum values of this function. This is the exact same function that we were working with before. So I'm going to go here, and I am going to say this. I'm going to copy all of this. I'm going to group it first off. Group. And then I'm going to copy. And I'm going to bring this over here. Nope, no. Edit, paste. Here. And I'm just going to make this a little bit smaller there. Okay. So this is where we were at, right, for this function. All we knew that it was increasing and decreasing. We didn't talk about any local maximums or minimums yet. However, now we can say with some certainty here, what's happening at -1? Is there a local maximum or a local minimum? Or nothing? Well, it's decreasing and then it starts to increase. What does that mean? Local minimum. So there's a local minimum at -1. We'll find out what the value actually is here in a second. Okay. In between, I guess that's at 0, right? What's happening at 0? It's increasing. So it was decreasing, shifted to increasing. And then I'm increasing from -1 to 0. And then at 0, I start to go back down. So what is that? Local max. And then here, something happens at 2. It goes from decreasing and then to increasing. So it was decreasing and then it started increasing. So that's a local minimum. Now, we then have to say, okay, well, I mean, it's useful to tell us where it happens, but the most important information is what the actual value of the function is, right? Find the local maximum minimum values of the function. What is it happening at? Now, you know how we went back into the derivative to tell us our ID test? When you go to actually figure out what the maximum and minimum values are, you have to go back to the original, okay? You have to go back to the original. That's why I didn't copy over the derivative. So I'm going to go back in and I'm going to say, okay, 3 times -1 to the 4th minus 4 times -1 to the 3rd. I'm going back into my original. I'm just plugging -1 into here. -1 to the 3rd minus 12 times -1 squared plus 5. So, oh, cool. So this is happening at -1 comma 0. This is local minimum at -1, and it is 0, right? So basically, there's a bottoming out point at -1 comma 0. There's a local maximum at 0 comma 5, right? If I plug in zeros here, that just gets me a 5. And then let's plug in 2. 3 times 2 to the 4th minus 4 times 2 cubed minus 12 times 2 squared plus 5. -27. I better check that. Did that pretty quick there. I get -27. Yep. Oh, look at me. I did synthetic division to find that on my paper.
Ew.
Whoa, throwback. That was fun. Okay. You can obviously just
So to find the
a critical, let's just go back through the process. To find the critical points, which is where we have to start, you set the derivative equal to 0. That will tell you where you should run your increasing decreasing test.
Yeah.
And then we just choose points to the left and to the right to the left and to the right and in between, basically. Mm-hmm. See where it's positive and negative, because that's where it's going to turn from increasing to decreasing. And that will inform us where the minimums or maximums are occurring, if they are. Increasing to decreasing means a maximum. Decreasing to increasing means a minimum. Increasing increase is nothing. Decrease is nothing. Then I take those values where they happen at and just run them through to see where it actually, like the actual coordinate occurs. X value, Y value. 10:45. Somebody's 10:45 alarm. Yep.
So when do you plug the numbers into the derivative? Because didn't you say that you plugged?
We plugged it back into the derivative when we were seeing whether it was going to increase or decrease. Like we plugged -2 into the derivative to see what the slope was doing.
Yeah. Okay. Because the derivative is slope.
Exactly.
Yeah. Got it.
All right. Let's do another one like that. But let's make it funky and let's do a trig one. Oh, it's not. So I'm only going from 0 to 2 pi, so 1 rotation. I know if I included all rotations, this would be an infinite set. But find the local maximum and minimum values for this function. Okay, so first step is finding the critical points, right? That's our first place that we got to start. So it looks like g prime of x is, okay, derivative of x is 1. Plus 2 times sine x. So the derivative of sine is cosine. 2 cosine x. So the derivative of x plus 2 sine x is 1 plus 2 cosine x. Now, the possibilities of being critical points are where this derivative does not exist or where the derivative is equivalent to 0. Is there any place where the derivative does not exist? No. This is trigonometric. And it's going to forever do this, right? Just basically with a vertical shift up 1 and then a vertical stretch by 2, right? So it's never going to be any discontinuities, right? It's just going to keep on going, especially from 0 to 2 pi. So it's just going to go like 1 iteration. Now, so it's always going to be defined. Well, then we have to look at where the zeros are. 1 plus 2 cosine x is equal to 0, right? I have to see where the critical points are. Subtract the 1. 2 cosine x is equal to negative 1. I divide by 2. Cosine x is equal to negative 1/2. And then I see, okay, well, cosine x is equal to negative 1/2. That means x is equal to inverse cosine of negative 1/2. So the question is, what angle gives us a cosine of negative 1/2? Okay, well, think about your unit circle here. Cosine is negative on the left side. So which one gives us a cosine value of 1/2? Okay, well, it's got to be either the 30 family or the 60 family, right? How do we think about this? Well, I want the x value to be 1/2, right? Remember that I always think of it long side, short side. Like if I look at this triangle right here, right? And this one would be equivalent down here, that coordinate down there as well. The x value is going to be the short side. The y value is going to be the long side, right? Radical 3/2 is bigger than 1/2. So the short side here is my 1/2. So the x value is 1/2, negative 1/2. So these are the two values that I'm going to want. Honestly, though, you could always double check it. Let's go inverse cosine of negative 0.5. It's going to get us this. Then we could just kind of got to test it out. Like, okay, I believe that this is, that's the pi over 6 family, right? No, pi over 3, right? Yeah, 1 pi over 2 pi over 3. I believe that is a 2 pi over 3. Am I right? Cross your fingers. Woohoo! 2 pi over 3. You can always double check it like that. All right, but that's not the only place, right? So this is equivalent to x is equal to 2 pi over 3, or, because there's another place where that occurs, 1 pi over 3, 2 pi over 3, 3 pi over 3, 4 pi over 3. I believe it's 4 pi over 3. See, I can't run that on my calculator, though. I just have to trust myself on that one, because the calculator is only going to give me the, that restricted domain. Cosine 0 to pi. All right, so 2 pi over 3 or 4 pi over 3. Those are my two values. I guess I could just double check one. Yeah, those are 2 pi over 3 or 4 pi over 3. Those are the only places where it could change from increasing to decreasing. So let's run my increasing decreasing test. I don't know why I put that right there. I don't like that. So let's run my increase decrease test. The only possibilities of changing are at 2 pi over 3 or 4 pi over 3. That's the only possibilities of it changing. So let's pick a point in between here, or on the left, in between, on the right. Now, you know what I'm going to do? I'm going to pick nice, easy points. I'm going to pick 0. I'm going to pick 2 pi. And then let's pick something in between. Pi. Those are numbers that you can easily run. But honestly, I could pick anything in between there, right? Now, I go back to my derivative, right? You got to remember to go back to the derivative for your increase-decrease test, because you're looking to see what's going on with the slope. Is it positive or is it negative? Positive means increase, negative means decrease. All right, if I plug 0 in, 1 plus 2 times cosine 0. Okay, cosine 0 is 1. So 1 plus 2 times 1 is 3. Do I care about the fact that it's 3? Not in the slightest. I care about the fact that it's positive. Then we run pi. 1 plus 2 cosine pi. Well, pi over here, the x value is negative 1, isn't it? So 1 plus negative 2. I don't care about the fact that this is going to come out to be negative 1. I care about the fact that it's negative. I bet that the next one's positive, but I don't know for sure. All right, let's plug in 2 pi. Well, 2 pi is the same as 0, so positive 1. So 1 plus 2, again, is 3. So it turns out positive. But yes, it is positive. Okay, so it goes positive to negative to positive. Now, it didn't ask me where it's increasing or where it's decreasing. Like, I don't have to define those intervals. I mean, I guess it's good. We could say, I guess we should go through the motions and say, well, it's increasing from going on our interval 0 to 2 pi over 3. It's decreasing in between from 2 pi over 3 to 4 pi over 3. And it's increasing again from 4 pi over 3. And then where does our interval stop? 2 pi. Okay. Because again, it's just one rotation. Before we had infinities because we didn't have a boundary. Okay, now we say, are there local maximums and minimums? Yeah. Okay, it's going from increasing, the function is going up, and then turning downward at 2 pi over 3. That's a local max. So this is a local max at 2 pi over 3. And then it goes from decreasing to increasing at 4 pi over 3. So a local minimum at 4 pi over 3. Now, we should run the numbers to see what those values actually are. And for that, I have to go back to my original, x plus 2 sine x. So we have the x is 2 pi over 3. X, 2 pi over 3, plus cosine, plus 2 sine x, excuse me, plus 2 sine x, plus 2 sine, 2 pi over 3. Right, x plus 2 sine x. 3.8. I'll just leave it at that. 3.8. It's probably some irrational number with a radical in it. And then let's see where the local minimum happens. Well, it happens at 4 pi over 3, but let's see what it is. You know what I'm going to do? I'm just going to copy and paste that and just change that into a 4 pi over 3. Oh, 1, 2, 4 pi over 3. 2.5. I'll round it to 2.5. That's the y values where those things are occurring. So I think you can see where we're headed. We're just going to now keep looking at functions without looking at the graph, kind of like blinders on. Don't show me the graph. And seeing, okay, where are those local minimums? Where are those local maximums? And just kind of exploring all different types of functions and seeing, okay, where do we see those local minimums, maximums? We are going to have some bending going on soon. And then tomorrow we'll actually talk about what does f double prime say. If f single prime says that increasing, decreasing, what does f double prime actually say? Okay, all right, we'll pick that up tomorrow. A little foreshadowing there, just to whet your appetites a little bit.